Okay, we are going to talk about connecting the graphs of f prime and f double prime. We did an activity talking about this, so the purpose of this lesson is just sort of to solidify the things that we talked about in the activity and that hopefully you took away from the activity, kind of formalize it, just so that it's all laid out clearly for you and in this video, then hopefully in your brain. So first thing we're talking about is called the first derivative test. Now we've been using the first derivative test for a while. As I mentioned, chapter 5 is a lot of formalizing things that we've already kind of been able to intuit. So it says this: if f prime changes from positive to negative, f has a local maximum at c. What does c mean? Well, I'll show you. Here's a couple ways that you can have a maximum. You guys are probably aware of a lot of this. So if this is our c value here, then there's a maximum there. You can also have it at a point that's not differentiable. So that is representing, this one is representing a maximum where the derivative would be 0. But you could also have a maximum that does something like this. Right, here's your c value, and there's a maximum there. Okay, so here the derivative would be positive, then it would change to negative. Here the derivative would be positive, and then change to negative. In both instances, you have a maximum. Okay. All right, in the second situation, if we have, this is where f prime changes from negative to positive, then there must be a local minimum at c. Okay, so you can kind of imagine what this would look like. Again, this is not showing you anything that's probably particularly earth-shattering. So maybe you have a minimum that looks like that. You could also have it be not differentiable. And so maybe you have something like this at c. Okay, so that is officially called the first derivative test, or the first derivative test for extrema. What if f prime doesn't change sign at a critical point? Well, there's a few ways that this could happen, and I want to show you a couple of them. One, the one that's probably come up in class more frequently, is if you have something like this, where here is your c value, and you have a horizontal tangent there, but actually you've got increasing on one side, positive derivative, and increasing on the other side, positive derivative. So the critical point there is not going to result in a maximum or a minimum. You can have a situation like this, and this is shows up less frequently in class, but is still the same kind of situation, where you have sort of this cusp thing, where you've got decreasing here, you have a cusp, and then you still have decreasing coming out the other side of that critical point C. So in both of these instances, in this instance here, you would have a sign chart that looks something like this. You'd have your C value, and then you'd have negative, negative. On your sign chart here, it'd be positive, positive. But so this is still a situation where we might not have a sign change at a critical point and might not have an extrema. Okay, so it's not just a horizontal tangent. This is not differentiable at this point. All right, so let's move on to number 1 here, where we find the intervals of increasing and decreasing. Use the first derivative test. First derivative test means we're going to need to use the product rule, because this is a product. We're going to take the derivative. By the way, we're doing this all analytically. I do have the graph over here, but that's just for reference in a second here. So I'm going to take the derivative, and so I will get this. G prime of x is equal to the first function, which is x squared minus 3, times the derivative of the second. Well, that's just e to the x. Plus the second, which is e to the x, times the derivative of the first, which is 2x. Okay, and then I'm trying to set this, I'm going to set this equal to 0, and then I'm going to solve. So I've got 0 equals this, and in this step, I'm going to factor out the e to the x from both of these terms. So I get this, e to the x, and then left over I'll have x squared minus 3, 2x. I'll just put that in order of the quadratic. So x squared plus 2x minus 3. And I'm relying on the zero factor property here, which says if you've got everything factored, you can set each individual factor equal to 0 to solve. So then this quadratic factors in this way. So I get e to the x, and I get x here, and then I think it's got to be numbers that multiply to give me negative 3 and combine to give me 2. So it's going to be x plus 3 and x minus 1. Okay, so there is my there's my function set equal to 0. So I will have critical points at negative 3, 1, and then when is e to the x 0? Well, if you do a little bit of work on that, you'll find that it's never equal to 0. So you either think of the graph of e to the x, or you can actually try to solve that equation. You'll end up taking the natural log of 0, which doesn't exist. Anyway, our two critical points then are going to be at -3 and +1. And then you pick points on each interval, right? So maybe we check -4. If you do that, you'll get a positive number. If you check 0, you plug that in, you'll get a negative number. By the way, I'm plugging into the derivative. Plug in a number like 2, you'll get a positive number there, okay? So that should imply then that you've got increasing, decreasing, so a max at -3, and decreasing, increasing, so a min at +1. And so I guess I'm not going to write that out explicitly because I don't have a lot of space here. But if you check the graph here, you do see that, right? You do have a maximum at -3, and you do have a minimum over here at 1. So we can confirm that graphically. Okay. All right, let's talk about concavity. Hopefully you watched the video where I kind of explained concavity in what you might say is pre-calc terms. But here we want to use calculus to define concavity. All right, so the graph of a differentiable function y equals f of x is concave up on an open interval if y prime is increasing. So y prime is increasing on that interval. What does that mean? Well, it means y double prime has to be positive. Excuse me. So concave up implies y prime is increasing, which implies the second derivative is greater than 0 is positive. Okay. So what does concave up look like? Well, it can look like this. These are just chunks of curves, right? It can look like this, and it can look like this. Okay. It's concave up, concave down. Looks like this. It could look like this. It could look like this. Okay. Those are concave instances of concave down. So here, if I have this function y equals f of x, then you can see that right here, I'm concave down, or it is concave down, until right about here it switches. So it's concave down here. Here it switches to being concave up. All right, so then if you take the first derivative, so if you take y prime, then you can see here that you get decreasing of the first derivative to here, and then increasing of the first derivative there. And then the second derivative, so this is y double prime. In the second derivative, we have negative here, and then it switches to positive here. I'm not sure why I wrote out positive there, but anyway, you get the idea. So the idea here is that concave down corresponds to decreasing in the first derivative, negative of the second derivative, okay? And then you can see the same thing for positive and up, all right? So I think that's it for concavity, at least on this page, so let's go to the back. All right, so now we're going to do this analytically, and again, I've given you the graphs just to confirm here instead of graphing them in the calculator. So we want to find the concavity of y equals 3 plus sine of x from 0 to 2 pi, all right? So first thing we're going to do is take the derivative and the second derivative, okay? Because now we're looking for concavity. We're trying to do it analytically here. So I'm going to take the first derivative, which is going to be cosine of x. And I'll take the second derivative, which is going to be negative sine of x. All right. So what does that look like? Well, negative sine, if you think about what the graph of negative sine looks like, and by the way, there's a couple ways we could do this. I mean, we could set negative sine equal to 0 and solve. But, I mean, the graph is probably going to be just as helpful. It's probably good to have either on the unit circle or the squiggly graph, or really both of these memorized. So, for instance, if you should be able to figure out that negative sine has intercepts at 0, pi, and 2 pi, because its period is 2 pi. All right, and negative means that the original sign would be flipped over the x-axis. And so you can see that this is what our second derivative looks like. So since the second derivative is negative from 0 to pi, we would expect the original function to be concave down on the interval from 0 to pi. And we would expect the original function to be concave up on the interval from, well, wherever the second derivative is positive. So from pi to 2 pi. Then we can also infer that there's a change in concavity here at pi, which will lead us into our next thing. So you can see that we have the graph of f, and we have the graph of f double prime here. So does our analysis pan out? Yes, it does. Here we have concave down in the original. Here we have concave up in the original, and you can see that the second derivative is above the x-axis. Here it's below the x-axis here. Okay. Let's talk about inflection points. Inflection points are a point where the graph of a function has a tangent line, in other words, it's differentiable, and where the concavity changes. That's what we call an inflection point. Okay? So here at pi, we would have had an inflection point. Again, because that's a change in concavity. We're going to take the second derivative and we're going to find where the sign changes. Okay, very similar to the first derivative test. In the first derivative test, you may not have a maximum or a minimum if the sign doesn't change at that critical point. Well, the same thing is going to be true for looking for inflection points. If you take the second derivative and you find a point where the second derivative is 0 or doesn't exist, then you may not have a point of inflection. Okay, if there's a change in concavity at a point where the second derivative doesn't exist, that is not an inflection point. There is a change in concavity. So what I'm thinking is like, so let's say that you have, just real quick, so maybe at x equals 2, you have concave up there, you have concave down there, right? This is not an inflection point here, okay? This isn't vertical asymptote. It does change concavity, but it is not an actual point. All right, so let's find the inflection points of this graph. We're going to do it analytically. Here we go. So first derivative, 5x to the fourth plus, I think it's going to be x, right? Yeah, plus x. Second derivative, so y double prime. That's going to be 20x to the third plus 1. We want to know when is the second derivative equal to 0. Those are possible potential inflection points, right? So 0 is equal to 20x cubed plus 1. I'm going to subtract 1 to both sides. I'll have negative 1 equals 20x cubed. Divide by 20, and then take the cubed root. So I end up with this. X equals the cubed root of negative 1 over 20. Right? So let's use a little sign chart here, analyzing the second derivative and where that second derivative is 0. So we're putting the cubed root of negative 1/20 on the line here. So this is a negative number, by the way. So you can pick a number to the right of it. So maybe you pick 0. You plug in 0 to the second derivative, you get positive 1. So you get a positive. You plug in negative 1 over here, you'll get negative 20 plus 1, which is negative 1. So you get a negative there. So it does look like we have an inflection point. The second derivative exists at this point, and there is a change in concavity there. Therefore, there is an inflection point. And really, we should put the actual point, x comma y, but this one doesn't come out very nice. On the quiz and the tests, I'll pick up a point that comes out a little bit nicer, and we'll let you use your calculator. All right. This one, you might try it on your own. I don't think we're going to do it in the video, but you might try to find the inflection points in y equals e to the negative x squared. This is the graph that is generated. You should get an inflection point right about here and an inflection point right about here. You can see we've got concave up, then down, then up. All right. And the second derivative test for local extrema, we're going to analyze that and learn about that in an activity that we'll do in class. So we're going to leave this blank for now. I do think at the end of the activity I tell you what to put in this box, but we are not going to do that in this very moment. So otherwise, that wraps up section 3, or at least what we're going to cover in this video on section 3.